Good morning. My name is Georges Mellon from EPFL in Lausanne. I'm in charge of the prize selection committee of the EAS, and today I'll chair the first part of this session related to the MERAC prizes. I remind everybody to not hesitate in nominating as many good people as you have for any of the EAS prizes, the Tycho Brahe, the Tritsis, and of course the MERAC prizes. And we'll start today with the first prize, the Theoretical Astrophysics MERAC prizes, which has been awarded this year to Aris Tritsis, who was in Greece for his PhD thesis, and he is now in Canberra in Australia. And the reason was for fundamental contribution to the physics of the interstellar medium of the process of star formation. Aris, you have the floor.
All right, can you all see my screen?
Perfect. You can start.
Perfect. All right, so hello everyone. First off, let me start by saying that I sincerely hope that you and your families are well and unaffected by the coronavirus situation. Before we begin, I would also like to say a very big thank you to the European Astronomical Society and the MERAC Foundation for this very special honor, and thank my PhD supervisor, Stasis, as well as the entire Department of Physics at the University of Crete for the continuous help and support throughout my PhD and to this day. And now, in this talk, I'm going to present part of the work that I did during my PhD and how this work brought me to the project that I'm currently working on, which I have named HOMERIC. So HOMERIC stands for Helios Magnetic Field as evident from striated interstellar clouds. And with this project, I aim to create a three-dimensional map, a three-dimensional atlas of the strength and the orientation of the mean component of the magnetic field in the galaxy. But before I go into the science, I first feel obliged to explain the acronym, for which I'm particularly proud of for two reasons. The first very modest reason is that according to the Oxford Dictionary, HOMERIC stands for epic and large scale. And the second reason why I like this acronym so much is that the word Homeric comes from the name of the ancient poet Homer, who wrote the Odyssey. And much like the journey of Ulysses to Ithaca, which is a small island in Greece and my hometown, finding the galactic magnetic field has been a real odyssey. Now, moving on to the science, I left something here that I didn't explain. I didn't explain what are striated interstellar clouds, or in other words, what are striations. So striations are these faint, ordered, hair-like structures which we see in the outskirts of molecular clouds. So in this slide on the left, I show an image of a molecular cloud, and the dense region here is surrounded by this network of striations, which are marked with the cyan arrows. But striations do not just appear in molecular clouds. They are in fact very common throughout the interstellar medium of the galaxy. And the figure on the right in the slide is an all-sky atomic hydrogen map. And as you can see, away from the galactic disk, most of the clouds appear to be striated. And striations have this amazing property that wherever they are observed, they always seem to be aligned with the magnetic field. So in this slide on the left, I show a region with striations from a molecular cloud. And the black segments here are optical polarization measurements showing the direction of the magnetic field. And as you can see, even by eye, striations follow the magnetic field very well. And the figure on the right is exactly the same thing, now quantified for another molecular cloud. So this is the distribution of the relative orientation between the magnetic field and striations. And as you can see, there is this peak at very small angles, indicating again the preference for alignment. And despite the fact that striations are very common throughout the interstellar medium, their formation lacked explanation for almost a decade after their discovery. So during my PhD, I performed a number of numerical experiments, testing out various formation mechanisms that could potentially have accounted for the formation of striations. And in this particular slide, I show the setup of my simulations for just one of these scenarios that I tested. And in this case, in this scenario, striations are formed as a result of fast magnetosonic waves. So on the right in the slide, I show an animation of the magnetic pressure in the simulation. And what is essentially happening here is that you have two magnetic field lines approaching each other, dragging the gas with them, creating compressions in the gas. And vice versa, when the same two magnetic field lines move away from each other, dragging the gas with them, they create rarefractions or underdensity in the gas. And having a spectrum of these waves with different wave numbers creates a complex pattern of overdensities and underdensities in the gas, which we end up seeing as striations. And in fact, these compressible fast magnetosonic waves can be excited through nonlinear interactions with Alfvén waves, which I show here on the left. So in this slide, I show the results from my simulations on the right. So this is a density snapshot along with observations on the left. And in order to quantify the results from my simulations, I also measured the mean contrast between adjacent striations. So for the parameter space that I examined, I found a value of 5 to 10% in the simulations, as opposed to 10 to 20% in the observations. So just for reference, for every other scenario that I tested that could have potentially accounted for the formation of striations, the mean contrast was no more than 10 to the minus 3%. And as a result, this model of fast magnetosonic waves stood out as the only one being able to explain their observed properties. And having such a model that can explain the observed properties of the structures is really important, is significant, but what's even more important is to actually use this model to make detailed predictions. And the first prediction that arose from my model for striations is that when you have waves and you have boundaries, these waves can get trapped and you can get normal modes. So in this slide on the left, I show a cartoon representation of a cloud with red cylinders representing striations, and the black arrows represent magnetic field lines, which assume to be along the Z direction. So for this sort of box-like cloud, the wave numbers of the normal modes will be given by the equation here on the right, where n and m are integers ranging from 0 to infinity, and Lx and Ly are the dimensions of the cloud perpendicular to the magnetic field. So I went ahead and attested my prediction towards the Musca molecular cloud, which is an isolated cloud in the southern hemisphere. And this is a really important cloud for two reasons. The first reason is that Musca is not actively forming stars yet. And as a result, by studying Musca, we can study the initial conditions for star formation. And the second reason why this is an important cloud is because of its elongated morphology as projected on the plane of the sky. People have always speculated that this is an interstellar filament. This was supposed to be the best example of a cylindrical-like cloud we can find in nature. So going back to my prediction of normal modes, I took cuts perpendicular to the long axis of striations inside this green box shown over here, and I computed the power spectra of these cuts, which you can see here on the left. So in this power spectra, I also identified the peaks, which are marked with the red dots, and I plotted these peaks as the black distribution shown on the right. So what this black distribution shows is the number of peaks at different wave numbers. Next, what I did is that I considered the value for the wave number in the first peak in the distribution, so that's the first red line. And in the equation on the upper right, I set n equals to 1, m equals to 0, and I found a value for Lx, which represents the length of the cloud on the plane of the sky. And then I repeated the exact same process, but for the second peak in the distribution, so that's the second red line. And this time I set n equals to 0, m equals to 1, and I found a value for Ly, which represents the depth of the cloud along the line of sight. Finally, I put the values for Lx and Ly back into that equation, and for different values of the integers n and m, I predicted analytically the wave numbers that should have been present if normal modes were indeed established in this cloud. So these analytical predictions are shown with the blue dashed lines, and as you can see, they fall right on top of the observations, so I was confident that normal modes are indeed established in this cloud, and that the values that I measured for Lx, the length, and Ly, the depth of the cloud, were accurate. And the final thing to notice from this slide is that the values for Lx and Ly are in fact comparable. So what this means is that Musca, which was once considered to be the prototypical filament, is in fact a seed-like structure, a pancake which we see edge on. So this was the first time that normal modes were ever observed in a molecular cloud as a whole, and the first time that we were able to accurately determine the three-dimensional structure of a cloud. Finally, we also converted the wave numbers, the spatial frequencies, into sound. So the movie in the next slide is the Song of Musca. Please enjoy. right? So this was a spectacular result, but in fact, the prediction for normal modes was not the only one. There was in fact a second prediction, which I think is even more important. So if we linearize the image equations, then we can arrive in these three expressions for the perturbed velocity, the perturbed column density, the perturbed magnetic field, because of the waves creating striations. And the first thing to notice here is that the exponential part right at the end is the same in all these three equations. So what this means is that if I were to take cuts perpendicular to the long axis of striations, then the power spectra of velocity, column density, and magnetic field should all peak at the same wave numbers. And the second thing to notice is that in the perturbed velocity, we have the amplitude of the waves appearing, so that's A n, as well as their frequency, that's omega n. And in the perturbed column density, we have again the amplitude of the waves, their wave numbers, K n, and the mean column density, which is denoted here as NH0. So if I further take the ratio of powers in the power spectra between velocity and column density, then the amplitude of the waves cancels out, and all I'm left with is that the ratio of powers equals omega over k over the mean column density. But from the dispersion relation of fast magnetosonic waves, we know that omega over k is approximately equal to the Alfvén speed. And if I further substitute the expression for the Alfvén speed, then I can arrive in this equation shown on the bottom right, which is a new analytically derived method for measuring the strength of the mean component of the magnetic field, and everything on the right-hand side of this equation are in fact observables. So by utilizing observations of striations, we have a new analytically derived method for measuring the strength of the magnetic field. And of course, I tested this analytical method with numerical simulations considering molecular cloud conditions. And the simulations also had non-equilibrium chemical modeling with a very extended network of 300 species and 14,000 reactions. And I also post-processed my results with a non-local thermodynamic equilibrium, multi-level, three-dimensional linear data transfer code that I developed called Pirate. So on the left in the slide, I show some of the results from the simulations. So the red lines are the power spectra of velocity cuts perpendicular striations. The black lines are the power spectra of column density cuts perpendicular striations. And from this set of power spectra, I was able to correctly retrieve the value of the magnetic field initially in the simulations. But what interests me more these days is actually the application of this method to H1 observations, and this also brings me back to Homeric. So on the left in the slide, I show again the power spectra of velocity with red and column density with black. And as predicted analytically, the power spectra peak nicely at the same wave numbers. And what is more, the variation in power in the velocity and the column density is similar. So from this power spectra, I can arrive in the plot shown on the right, which shows the frequency of the waves omega as a function of their wave number, and what is essentially an observational derivation of the dispersion relation of fast magnetosonic waves. So if I find this relation for striations in a cloud, then my model is ipso facto verified. And from the slope of this relation in linear scale, I can find the Alfvén speed, and in turn, I can find the value of the magnetic field. And vice versa, if the structures in a cloud do not obey this relation, then I cannot say anything regarding their formation, nor can I measure the magnetic field. And this is really important because this way I avoid false positives. So this method can only be applied where its assumptions hold. But in fact, in this slide, I show the results from just one cloud, whereas I have applied this method to two clouds located along the same line of sight and perform magnetic field tomography. And this is exactly what I show in this slide with the locations of the clouds in the galaxy. And what's interesting here is that the values that I found for the magnetic field, so that's 20 and 50 microgauss, were a factor of 3 to 5 higher than what galactic magnetic field models predict. And now that I have the proof of concept established, I figured to myself, why not do this for the entire sky? So the first step in applying this method to the entire sky is to actually identify individual clouds and striations within these clouds in individual lines of sight. And to this end, I have developed an automated algorithm to perform a Gaussian decomposition of all spectra in position-position velocity data cubes. So on the right in the slide, I show an integrated position-position velocity data cube, and each pixel here contains a spectrum with 4 examples shown with the black lines on the left. And the red lines here are all the components that I have identified in my Gaussian decomposition added up together. And as you can see, they fit the observed spectra really well. So once I have identified all of my components, then for every component, I can go ahead and I can calculate its velocity map, its first moment map, its column density map, and a map that entails the orientation of structures that are evident in the column density. And this is exactly what I show in this slide. This is just an example for just one of the components that I have identified, with the velocity on the left, the column density in the middle, and the orientation map on the right. So from these three maps for every component, I can then compute average values, and I can plot all of my components in the three-dimensional space of average orientation, average velocity, and average column density. So each point here is computed from the three maps and similar to the three maps shown in the previous slide. So once I have this plot, then I can utilize a clustering algorithm to cluster my components back now into individual clouds. For this particular region, I have identified 4 clouds, the individual components of which are shown with the different colors. And the distance to each cloud will be given by 3D dust reddening maps. So the end result from all of this will be the creation of a 3-dimensional map of H1 clouds in the galaxy. And once I have this map, then I can go ahead and I can find striations within individual clouds now. I can measure the orientation and thus measure the orientation of the magnetic field, since the 2 are always aligned. And I can apply my method to measure the strength of the magnetic field. So this way, I will create a 3-dimensional map, a 3-dimensional atlas of the strength and the orientation of the plane of sky component in the galaxy. And as I'm sure you know, having these two maps would be really important for a number of areas within astrophysics and cosmology, including ultra-high energy cosmic ray propagation studies, the removal of galactic foregrounds to CMB polarization experiments, and the list goes on and on. So precisely because of the importance of these questions, I really do think that the goal of creating a 3-dimensional atlas of the strength and the orientation of the magnetic field in the galaxy is a really worthwhile one, is a journey worth taking, and with Homeric, I'm here to achieve this. So thank you very much for your attention.
Thank you very much for these very interesting talks. Sarah, I do not see any question. However, some other people have problems, and I received a question from Lucio Mayer, who is a member of the board of the MERAC Foundation. So I'm going to start with him, and then I'll give maybe the opportunity to Sarah to ask other questions if we still have time. So first question, turbulence would affect the propagation of MHD waves and generically blur sharp boundary. How is turbulence accounted for in the models? Is that just self-generated as MHD turbulence, or is that generated also by other mechanisms like supernova explosion or graviton turbulence?
So specifically for Musca, there is no supernova explosions nearby. A number of simulations have shown that striations only appear in subalvenic turbulence. And in fact, subalvenic turbulence with a superposition of MHD waves is basically indistinguishable, and a superposition of MHD waves is what I've been talking about all this time. So in the simulations, we only have MHD waves.
Okay. And another question, does the presence of normal modes, which clearly are not damped, allow to place constraints on the degree and nature of turbulence?
I haven't actually thought of that. But again, in the picture of Musca, the cloud is collapsing along magnetic field lines with MHD waves propagating in the direction perpendicular to the magnetic field. And in fact, I'm not sure, to be a bit provocative, I'm not sure if turbulence is in fact important for Musca. Line observations, spectral observations have shown that Musca is not turbulent. It is in fact a sonic-like structure. So yes.
Thank you. So Sarah, do you hear me?
Yes, you don't see the questions? I'm putting questions to you. Oh, sorry. So can I ask the questions?
Yes, read them, please.
Okay, maybe mute yourself, Georgia. There's a lot of echo. Let's see. Okay. So a question that comes from Ciro Pinto. He says, brilliant idea about the pancakes. I suppose that statistically some should be observed face on and appear much broader. Are you aware of any examples in a galaxy?
So there are some examples of clouds which are supposed to be seen as illuminated from cosmic rays. But I think that if they were seen face on, then it would be much harder for us to notice them, because the column density would be smaller.
All right. Another question that comes from Marco Dart. How will future missions, such as, for example, JWST or SPICA, can help in the study of star-forming regions and turbulence?
So I think HOMERIC is really connected with SPICA and other future missions, including PACIFY. The advantage here is that, compared to SPICA, is that I can do this. I can measure the magnetic field in a tomographic like manner. So I won't just measure the integrated polarization, but the two are definitely complementary.
All right, we have another question from Alvaro Sanchez Monge. Actually says he has a couple of questions related to the Gaussian fit of the spectral H1 features.
Yes.
First, how do you deal with the absorption features in the H1 lines?
I don't have a good answer to that yet. So this is all preliminary.
Second question, how do you assign which velocity component is related to each other velocity component in another pixel?
So this is why I do the clustering. So I find all of my components, and then it's not enough to just measure clouds in just velocity. That's why I find the orientation and the column density, so that I can cluster components to clouds. So I don't do that. I let the clustering algorithm tell me how many clouds are there.
There are no more questions.